A power transformer is a massive, multi-million-dollar asset. It sits at the grid's heart, stepping high transmission voltages down to usable levels for cities. When a short circuit occurs, you have mere milliseconds to isolate the equipment. Any delay allows thermal runaway and extreme mechanical forces to tear it apart. The legacy approach to protecting these assets involved massive analog control panels. Upgrading or repairing a single relay in these older systems required technicians to spend hours manually tracing and disconnecting a maze of live copper wires. This traditional maintenance poses a lethal risk. Accidentally leaving the secondary wiring of a live current transformer open under load generates deadly high voltages that can instantly destroy insulation and cause fatal arcs. The modern solution to this physical bottleneck is a withdrawable unit design, like the RET615 protection relay. It operates similar to a hot swappable drive in a server rack. As the technician pulls the chassis out, internal mechanisms automatically close and short the current transformers. The external wiring stays secured to a fixed terminal block, meaning live wires are never manually handled. This mechanical design protects both the operator and the grid. It condenses a highly dangerous 6-hour maintenance window into a safe 15-minute swap, keeping the transformer's protection systems online longer. The relays are only as good as the data they receive. Traditional iron core current transformers hit an invisible ceiling during massive faults. The iron physically cannot carry any more magnetic flux, so the signal flattens out, blinding the relay right when the fault is most destructive. Modern digital switchgear replaces the iron with air. Rogowski coils are air core sensors that measure the magnetic field directly. With no iron to saturate, they maintain a perfectly linear, undistorted measurement, no matter how high the current spikes. Those pure analog signals are captured directly at the source. A local device called a merging unit instantly digitizes the waveform into precise data packets, known as sampled values. These digital measurements completely replace the miles of heavy interpanel copper wiring. The sampled values are broadcast across a single fiber-optic Ethernet network using an industry standard known as IEC 61850-9-2LE. Migrating from physical copper to a shared digital process bus clears out tons of wiring weight and ensures the relay processes clean, uncorrupted data. A digitized network introduces a new point of failure. If a single fiber-optic cable is cut or a switch drops a packet, it is functionally identical to severing a physical copper wire. The relay loses its signal. To counter this, engineers utilize advanced fail-safe protocols designed to prevent any interruption in the data stream, PRP and HSR. This diagram illustrates Parallel Redundancy Protocol, or PRP. The sender takes every data frame and transmits an identical copy simultaneously down two completely separate physical networks. If one entire network goes down, the relay continues operating on the duplicate frame that arrives on the surviving network. During normal operation, the receiver simply processes the first packet and silently discards the duplicate. High Availability Seamless Redundancy, or HSR, operates on the same logic, but uses the closed-loop ring topology shown here. It sends data in opposite directions around the loop, so a break anywhere in the ring still allows the message to arrive from the alternate path. Standard IT networks require time to detect a broken link and reroute traffic. Because PRP and HSR send redundant data simultaneously, they achieve zero switchover time. The protection system never suffers a dangerous communication delay. All of this pristine, redundant digital data flows into the relay's internal algorithms. The most rigorous test of these algorithms occurs at the generator transformer block. A spinning generator presents unique failure physics. If a fault occurs on the grid, opening a breaker stops the energy flow, but a generator carries massive mechanical momentum. Even after disconnecting from the grid, the spinning rotor continues pumping extreme fault current into the short circuit. Fully clearing this fault requires a coordinated master trip. The relay must simultaneously fire commands to open the grid side breaker, open the generator breaker, and shut down the generator's magnetic field to completely starve the fault of energy. But high-speed sensitivity creates a risk of false positives. Simply energizing a large transformer pulls a massive, chaotic spike of power from the grid. This is called magnetizing inrush, and to a basic sensor, it looks exactly like a violent short circuit. To prevent a false trip, the relay scans the waveform. An inrush current produces a specific high-frequency ripple known as a second harmonic signature. By identifying that exact frequency, the algorithm confirms the transformer is safely waking up, not failing. Flawless hardware and zero-latency networks only protect the grid if the relay's algorithmic logic can accurately distinguish a routine operation from a critical threat. Even with perfect logic, the physical equipment can fail. A relay can detect a genuine fault and issue the correct trip command, but the heavy mechanical circuit breaker might simply jam and fail to open. When this happens, a fail-safe called breaker failure protection takes over. The relay monitors the line after sending its trip command. If it detects high current still flowing milliseconds later, it registers that the primary breaker has mechanically failed. The relay immediately escalates the response across the network, sending new commands to adjacent upstream breakers to open. This sacrifices a larger section of the grid to sever power to the compromised zone. To catch these mechanical issues early, the system continuously runs trip circuit supervision. It passes a harmless monitoring current through the physical trip wiring, sounding an alarm if the connection degrades long before a fault ever occurs. Modern digital substation protection is a deeply integrated ecosystem. From hot-swappable physical hardware and zero-latency networks to the intelligent code overseeing breakers, every layer is engineered to guarantee the grid survives.